Okay, so welcome to this video tutorial. We're going to go through 3 midterm reviews for the upcoming Regents, the Regents Physics midterm. So this first section is more operational definitions. So I'll kind of just walk through some of them, talk about, highlight some things. The conversions, I'll leave it up to you to kind of take a look through the work and then come and see one of the physics teachers if you have any questions. And then when we get onto the multiple choice and free response sections, I'll step through each part. So for the first section here, we have a bunch of different quantities, and you're asked to put the proper units as well as record whether it's a vector or scalar. So for the quantities that you have heard of before, those are the quantities that are most likely to be scalars. So, and actually I'm just seeing a correction right here. This speed is actually a scalar. Okay, so if you are talking about a speedometer or you're traveling at some sort of speed, by definition it is the distance that you travel, the total distance that you travel divided by the time, and its units are meters per second. Acceleration being a vector and also meters per second squared. Force, the direction of how hard you're pushing, is a vector and the units are Newton. And for the Regents exam, you do need to know that it is a kilogram meter per second squared. Height, I'm going to actually add in heights are just distances. Those are the scalars. Momentum, for some of the classes we haven't quite yet talked about momentum, but we will prior to the midterm, so I'll just leave that blank. And likewise with impulse. Velocity being a vector, the loose definition of it you can think of as that it's speed with a direction, but more importantly, you'll see this on one of the first few problems, it is a displacement divided by the time. Okay, so it's the vector displacement divided by the time. And like speed, its unit is meters per second. Distance being a scalar, nothing to talk about there. Mass, time, scalar. Coefficient of friction, it is a unitless number, so actually you can even add in here that it is a scalar. Centripetal acceleration, just like any other acceleration, it's a vector. Centripetal force, like any other force, is a vector. Weight is a force of gravity, so just like centripetal force, it is also a vector. And its direction is always towards the center of the earth. Friction is a type of force, so it's a vector measured in newtons, and displacement is a vector measured in meters. Alright, I'll pause over this video for a moment. Feel free to pause at home and take a look through these. Alright, so getting on with the problems, we have a car traveling 90 meters due north, okay, in 15 seconds, and the car turns around and travels 40 meters due south in 5 seconds. What is the magnitude of the average velocity? So first off, let's just talk about this word magnitude. Magnitude means how big, how fast, how much. Okay, so in other words, you're really just looking for the value of the velocity, not concerned about what is the direction of the velocity. But remember that velocity, as I just mentioned, is a displacement divided by time. So what we want to first find is the displacement traveled, and actually I'm even going to add in total time. Okay, because here we have 2 times, so we want to know the total time. So we're traveling 90 meters north. Okay, then we're turning around and we're traveling 40 meters back the other way. So the displacement is your change in position. So you go 90 up, you go 40 back, so you're left off with 50 meters. And it's 50 meters north, but once again, we're just talking about the magnitude of the velocity, so we're not concerned about the direction. So displacement over time, we have 50 meters, and then dividing by, so 15 seconds and 5 seconds, so a total of 20 seconds. So 50 over 20, we get 2.5 meters per second. Okay, so the next one. We're taking a look at 2 cars, A and B, are 400 meters apart. Car A traveling due east at 30 meters per second on a collision course with car B, which is traveling due west at 20 meters per second. So how much time elapses? So we're going to use the definition of velocity as a displacement divided by time. Okay, we're going to do a little bit of algebra, so you can think of its velocity over 1, or it's perfectly valid to say I'm just going to flip these two variables. So I get time is equal to the distance divided by the velocity. Now the distance is easy, it's 400 meters, nothing to sweat there. But this velocity, so you start saying, all right, do I use the 30, do I use the 20, do I have to do something with the two? The easiest way to think about this is think about a approach velocity. So if one is traveling 30 one way and the other one's traveling 20 in the opposite direction, you could think of them as they're approaching each other at 50. So the velocity that you would want to put in is the 50 meters per second. And then throw this in, right, 40 over 50, so we get 8 seconds. Okay, so 8 seconds has gone by in order to until they actually collide. Next one, we have a baseball pitcher is throwing a fastball at 42 meters per second. If the batter is 18 meters away from the pitcher, how much time? So once again, we're going to take a look at our definition of average velocity, do a little bit of algebra, and we get time is equal to distance divided by speed. And this one's more straightforward, just a plug and chug. So we have 18 meters divided by 42 meters per second. And if you do that, we get 0.43 seconds. All right, on to the next one. We have an average velocity. The average velocity of an object during 6 seconds is 2 meters per second. What is the total distance traveled? So start off with our basic definition. Average velocity is distance over time, or displacement over time. And now we're solving for d. So our d is our average velocity times time. Plug in our 2 meters per second times our 6 seconds, and we get our 12 meters. All right, so here we get a little bit more into our kinematics, and for these problems here on out, I'm going to write down all the givens. So we go uniformly from an initial of 2 meters per second to a final of 7 over a distance of 12 meters. Okay, so what we want to know is the magnitude of the acceleration. So the acceleration is our unknown. So what you'll notice is that we do not have time as a given piece of information. So you're going to take a look at the timeless equation, and that is a Vf squared equaling Vi squared plus 2AD. All right, we're solving for A, so we have to do a little bit of algebra. We subtract the Vi squared. Okay, that equals 2AD, and then what you do is we divide by 2 times D. That should be a D. So it's Vf squared over 2D, excuse me, minus Vi squared over 2D. Okay, plug in our numbers. We have 7 squared minus 2 squared over 2 times 12. Plug her in, and you should get 1.9 meters per second squared. All right, next one. An object with initial speed of 4 meters per second. So I'm just going to write this down as we go. Accelerates uniformly to a final speed of 2 meters per second. Oh, sorry. Accelerates uniformly with an acceleration of 2 meters per second squared. Okay, in the direction of its motion. So that what that means is that it's going to get faster, and it does so for a distance of 5 meters. Okay, same idea. Timeless equation, we're asked now for the final speed. Okay, so we're going to use the timeless equation, Vf squared equals Vi squared plus 2AD. And of course, algebraically, to get Vf by itself, just square root. And just do that to both sides. Plug in some numbers. We have 4 squared plus 2 times 2. And that, of course, is the square root of that. So maybe you could do this in your head. 4 squared is 16. 16 plus 4 is 20, and radical 20, oh, I'm sorry. It's 2 times the acceleration times the distance, so it should be times 5 here as well. Okay, so 2 times 2 is 4, 4 times 5 is 20, 20 plus 16 is 36, square root of 36 is 6 meters per second. Okay, so that's our final answer. All right, next one. So 7, it says an object initially at rest, so that is initial velocity of 0. I'm just going to put a line in here. Shouldn't be through it. Accelerates at a rate of 5 meters per second squared and attains a speed of 30 meters per second. So VF is 30 meters per second. Okay. What distance does the object move? Okay. Once again, notice that we do not have time. So we're dealing with the timeless equation, equals VI squared plus 2AD. We're doing the distance, so D is equal, I'm going to do a little bit of algebra all in one step here, VF squared minus VI squared divided by 2 over A. Plug in some numbers. My initial velocity is 0, so actually I'll just get rid of that. So we have 30 squared over 2 times 5. And if you plug that in, you should get 90 meters. Okay, so the next one, now we have some multiple choice, so maybe we'll show some tricks on how to do this a little faster. So a rocket is initially at rest, so VI equals 0. It lifts off with a vertical acceleration, a constant vertical acceleration of 2 times 10 to the 1 meters per second squared, which, by the way, is just 20, right? 20 meters per second squared. How long? So we're looking for time, so now we're asking information about time. We'll reach an altitude of 9 times 10 to the 3 meters. So even if you say, all right, well, altitude, what are we talking about, what quantity? Use the units to help you out. So we have a distance of 9 times 10 to the 3, which is just 9,000 meters. Okay, so now if you look at your kinematics equations, we have a D, a VI, A, and a T. So that's going to be the fourth equation. So D equals VIT plus 1/2 AT squared. And notice that since our initial velocity is 0, 0 times any time is 0. And so we're looking for T. So we have D on this side, we have T squared on this side. So I'll first multiply both sides by 2. That gets rid of the 1/2. I divide by A, and then square root. So the square root of 2D over A is our time. And if I plug in some numbers, 2 times 9,000 divided by the acceleration of 20. Throw that into your calculator. I got a value of 30 seconds. Okay, which then, okay, that's 30 seconds. So now we have to match up our choices, but there's only one choice that has a 3 in front of it, so it's choice A. All right, a rock falls from rest. So VI equals 0 from off a high cliff. How far is the rocket fallen when its speed is 39.2 meters per second? So you will have a final velocity. It's saying how far. So that's a distance is what we're asking for. And you might be saying, I only know 2 pieces of information. How can I go about solving this? But don't forget that we're talking about an object in free fall. So we know the acceleration on Earth is 9.81 meters per second squared. So you actually know 3 pieces of information. So once again, we have a timeless equation. VF squared equals VI squared plus 2AD. Once again, we're solving for the distance. The initial velocity is 0, so let's get rid of that. Divide by 2A, and then we'll plug in some values. So D is equal to VF squared, so 39.2 squared, divided by 2 times 9.81. Okay, and you might be noticing too, by the way, that I am being very sloppy with my units here. So on a free response question, you would have to put meters, seconds here, meters per second. That should be meters per second. meters per second here and meters per second squared here. Just for the sake of this video, I am being a little bit sloppy with my work. Okay. I actually don't have this solved for, so give me just 2 seconds to throw this into my calculator. So 39.2 squared divided by, okay, I got a height of 78.3 meters. Okay. All right, number 10. It says a freely falling object near the Earth's surface travels downward at a constant. Okay, so nice. We have a conceptual question here. So freely falling object near the Earth's surface, so the acceleration due to gravity on Earth is 9.81 meters per second squared. Notice that you see the 9.81 here, but that's describing the velocity. What this means, once again, is that it is gaining 9.81 meters per second for every 1 second of fall time. Okay, so this is not the velocity, this is how quickly it's changing its velocity, and that's a distinct difference. And if you are unsure on that difference, please come talk to one of the physics teachers. All right, number 11. A rock is dropped off a bridge. It takes 5 seconds to hit the water. Approximately what was the rock's velocity just before impact? So it is dropped. Okay, so that is that gives us numerical information. That means it starts from rest. It doesn't say that it's thrown downward. It takes 5 seconds to hit the ground. We know the acceleration due to gravity is 9.81 meters per second squared. And we want to know the velocity just before impact, so we're looking for final velocity. So do a little bit of matching game in your reference tables, and you will find VF equals VI plus AT. This is 0, so we have 9.81 times 5. And that, of course, is 49 meters per second. Okay, if you had 50 here, if you called G to be 10, that's fine as well. All right, on to page 3. As shown in the diagram below, an astronaut on the moon is holding a baseball and a balloon. Okay, so if the astronaut releases both objects at the same time, what does the astronaut observe? Okay. So, you might be thinking that the baseball is heavier than the balloon, and therefore it's going to hit the ground first. And the problem with that is that although it is heavier, now that you have a better idea on the laws of motion, although it is heavier, it does have a bigger F net. So the acceleration is F net over m. But if it has a bigger F net due to the force of gravity, which is calculated mg, it is also going to be harder to move. That's what this term here means. We might say that it has more inertia, so it is more challenging to move. And algebraically, you will see here that the masses cancel out, and just verifying what we observed with dropping the bowling ball and the soccer ball out the window is that they accelerate at the same rate. So the baseball and the balloon fall at the same rate. Choice C. All right, so here we got some more calculations. It says an object starting from rest. So starting from rest, VI equals 0, accelerates at a rate of 3 meters per second squared for a time of 6 seconds. The velocity at the end, so the final velocity is what? So we have VF equals VI plus AT. And if we take the initial velocity, which is 0, we have A times T, we have 3 times 6, and that, of course, is 18 meters per second. All right, next one. A car is accelerating at 4 meters per second squared, so A equals 4 meters per second squared. It starts from rest, so skipped over that. That's 0. It will reach a speed of 28 meters per second. At the end of, so this is a little tricky, we're asking for a time. So use the same equation, VF equals VI plus AT. VI is 0, so cross that off, and then so we just need to divide by A. So the time is the final velocity, which in this case is 28 meters per second, divided by the acceleration of 4. And that is, of course, 7 seconds. All right, next one. And by the way, I am going rather fast through these, so if there's any questions that you need to kind of pause, think about, rewind, please feel free to do so. All right, so the speed of the wagon increases from 2 meters per second to 9 meters per second in 3 seconds. So the initial velocity is 2.5. The final velocity is 9 meters per second, and it does so in 3 seconds. And we want to know what is the magnitude of the acceleration. So once again, here's that word, magnitude. We want the number, we don't care about the direction. So A equals the change in velocity over time, okay? And so the change is 9 minus 2.5, final minus initial, divided by 3 seconds. If you throw that into your calculator, you should get a value of 2.2 meters per second squared. Next one, a 1 kilogram ball is dropped from the roof. What is the from a 40 meter tall roof? What is the approximate time of fall? Okay, so notice this does not change anything. This is a distractor. Mass does not affect acceleration, but it is dropped. That is relevant. So the initial velocity is 0, and it's a distance, a height of 40 meters. What is the approximate time? Okay, once again, we know the acceleration is 9.81 meters per second squared. So d, vi, a, and t, we have our d equals vit plus 1/2 at squared. Okay, the initial velocity is 0, so cross that off right away. Once again, we're looking for time, so we'll do the same tricks. We'll multiply by 2. We'll divide by a, and then square root. So we get a time is equal to the square root of 2 times 40 divided by 9.81 meters per second squared. So throw that into your calculator. I got a value of 3 seconds. Approximately 3 seconds. All right, how far will a brick starting from rest, so VI is 0, fall freely, so the acceleration is our good old 9.81, and we have a time of 3 seconds. And we're asking for how far, so we're looking for a distance. So same equation, just now it's a little bit easier because it's already solved for what you're looking for. So the initial velocity is still 0, so we plug in 1/2 times the acceleration of 9.81 times the time squared of 3 seconds squared. So I got a value of 45. All right, 19. An object is allowed to fall freely near the surface of the Earth. So our good old acceleration of 9.81, fall freely. The object falls a distance of, that's d, 54 meters in the first 3 seconds. 3 seconds. And we want to know what the so we don't know what the planet is, so we're looking for the acceleration. And you know, something that is implied here is that it starts from rest. Okay, it's dropped. So d equals vit plus 1/2 at squared. The initial velocity is 0, so that crosses off. Now we're looking for the acceleration, so we're going to do the first trick, first algebraic step, multiply by 2. But rather than dividing by a like we've done previously, we're going to divide by t squared. So the acceleration becomes 2 times the distance divided by t squared. So this is 2 times 54 divided by 3 squared. Plug that into your calculator. I got a value of 12 meters per second squared. Okay. An object is allowed to fall freely. Okay. So dropped from rest near the surface of a planet. The object has an acceleration due to gravity, a, of 24 meters per second squared. How far will the object fall in the first second? So be careful here, right? So that tells us a time of 1 second. So we're looking for how far, so we're looking for d. Okay, so same equation we've been using, d equals VIT plus 1/2 AT squared. Initial velocity is 0. Plug in 1/2 times the acceleration of 24 times 1 squared, which of course is 12 meters. Okay. All right, one more, and then we'll move on to the graphs. Okay, a 4 kilogram rock and a 1 kilogram rock fall free from rest from a height of 100 meters after they fall for 2 seconds. The ratio of the rock's speed to the stone speed. Okay, so notice that the mass is different, right? But they're dropped, and mass does not affect acceleration. So they're going to both accelerate at 9.81, so meaning at any moment of time, they will have the same speed, or a ratio of 1 to 1. All right, so I take a look at these. I'm actually going to change the color here. Explain the motion that would produce each graph. So what we want to do is take a look at what the object's doing, and more importantly, what does the slope of these graphs represent. So the slope of the displacement time represents the velocity. Okay, so what we can take from this is we can answer, what is the slope doing? Okay, and we're going to use some tangents here to identify that. And then that will tell us what the velocity is doing. Okay. Okay, so let's take a look at this. We have a slope here that's low. It is getting steeper and then steeper. So the slope is increasing, so that tells me that the velocity is going up, so the v is going up. Okay, and it's doing so in a constant fashion. So what we say is that this is a constant acceleration. Okay, and so you can kind of think of this, oh, maybe it's like free fall. Okay, here we have an object that has a constant slope. Okay, so what this means is that it has a constant velocity. So this is not only a constant velocity, but we can even say it's a constant positive velocity. Okay, here we also have a constant slope, so we have a constant velocity, but here notice the slope goes down to the right, so this could be a constant negative velocity. Okay, here we have a little trickier of a graph. Okay, so we start off steep slope, sometime later there's no slope, and sometime later there's a steep negative slope. So this object's going from a positive velocity to 0 velocity to a negative velocity. Okay, and so this is an object that is, slowing down, then stopping, and then speeding up in the opposite direction. Okay, and so your classic example of this is an object thrown up. So if I take a ball and I throw it up and it comes back down, it is going to slow down, it's going to come to a stop, and then it's going to pick up speed in the opposite direction. Okay, so any object that's thrown up and allowed to fall freely is going to exhibit this type of graph. Slow down to a stop, then speed up. Okay, so on the velocity time graphs, which these last four deal with the velocity time graph, the slope of this graph represents the acceleration. Okay, so if you ask yourself what is the slope doing, that will answer what is the acceleration. Okay, so this is a constant positive slope, so this is a constant positive acceleration. Okay, so this could be an object, speeding up in the positive direction, or it could be an object that is moving in the negative direction and slowing down with a positive acceleration. So anytime that your velocity and your acceleration are in the opposite direction, this equates to slowing down. And this is true all of the time. It's always nice to say those, always. Anytime your velocity is in one direction and your acceleration's in the same direction, this equates to speeding up. Okay, so this is always good to remember, these sign conventions. Okay, so here we have a constant negative velocity. Okay. Now I know that it's a constant velocity because the slope of a horizontal line is 0. So that means the acceleration is 0, which means that it's either doing not moving, or in this case, since it's a non-zero velocity, it's a constant negative velocity. All right, so here is a tricky one. Okay, so notice that, first of all, what I could say is that there's a constant positive acceleration. So likewise, this one has a constant positive acceleration. But we will notice that it starts off with a negative velocity. At some time it has a 0 velocity, and sometime later it has a positive velocity. Okay, so notice that it went from a negative direction to a positive direction. So this is an object turning around. Okay, and it is very similar to this previous one up here, but notice that up here we went from a positive velocity to 0 to a negative velocity. So this could be like we saw this in class with the fan car, pushing the fan car and the fan blowing in the opposite direction, or in this case the positive direction, but starting to move in the negative direction. Okay. And finally, the last one, we have a slope of 0, so this tells us an acceleration of 0, and this is a positive velocity, so this is a constant positive velocity. So be careful with this word constant, because a constant velocity and a constant acceleration equate to two different types of motion. Okay, so I hope this was helpful, and stay tuned for the next two videos. I'm not going to say that they're going to be short ones, but hopefully you just thumb through the ones that were relevant to you. Okay, thanks for your attention. Good luck studying, and we will see you soon. All right, good night. Bye-bye.